Okay. Good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up where I was last day. So last day we had seen how we can use the pumping lemma to prove languages are not regular, which was kind of fascinating in its own right. So I'm going to do another example with you here. I did put in the notes another example. So if you want to see how you could do things with palindromes, these are strings you could read from front to back, back to front. I gave an example with odd length palindromes, and also give you an idea of how you could try approaching it with an even length palindrome. So you can use these ideas to prove non-regularity. Now I want to show you a little bit of a trickier one, just because I have to make sure I show you at least one of these, and the way it's described is a little bit different from the other things. So I recommend you just think about this a little more carefully. So I'm going to do another example with you. Let me just switch my marker. This one I'm not very happy with. Just gonna boop. It bounced off the ceiling. That was pretty epic. Anyways, let's do this. So here's another example. So consider the language. So let's consider the following language. I'm gonna call it LS. LS. Sounds like something else, but LS, I'm going to call this that, where the strings are going to have the form of 0 to the I, 1 to the J, such that I is greater than J. So you should see right away that this one's a little bit trickier. Why? Because notice that I don't have complete freedom over the first symbol and the second symbol. They actually are kind of related to one another. So you always have to keep in mind this part of how I define the set of language. Sorry, our language. So we just got to be careful when we do this. So let me just head back in over here. Let's see. Is everybody still there by any odd chance? The power went out again. That was kind of strange. Okay. Am I still here, everybody? Just want to make sure. The power, it did the thing again. I just want to make sure I'm here. This is a funny day, man. It's a funny, funny day. Just connecting here. What a funny day. Just connecting here. I don't know what's up with today. Today's been a very strange day for me. Okay, here we go. Excellent. I have returned. I have returned. Let's see. Can everybody hear me fine? For some reason, it happened again. So let me just get things back over here and let's get back on things here. Sorry about that. So let me just close that. Can everybody hear me still? The internet the power did its thing again. I've never had this happen before. Okay, good. I'm used to other technical glitches, not just the whole power going out. So let me just, so I think I got everything here. Okay. The fun thing is that if you watch the recording, you're going to hear me rambling about other things while we're doing this. So let me... So first, let's make sure I got everything here. I think we're good. Am I looking fine over here? Just want to make sure. I apologize for the delay, everybody. Okay. So we're going to prove the following theorem, and let's cross our fingers the power doesn't go out again. If not, I will come back. So we're going to prove that LS is not regular. So what am I going to do? I'm going to use the same setup I've done before with the pumping lemma. So I'm going to use it to break the language. So I'm going to show you there's a string I can't pump. So first I just assume that language LS is regular. And of course I assume this so that I could get a contradiction. So what does that mean? That means that there's this constant, right? Then from the pumping lemma, there is a constant P that satisfies its conditions. So you might ask, Dan, what do I pick for the string this time? Because look at this, I have an I and a J. Now, we have to be a bit careful with this. Because remember, I is strictly bigger than J, so I'm going to make sure I select a string that's indeed in this language. Does anybody have any suggestions of a string I can use? And remember, the whole trick is I want to try to make sure all the first P symbols are going to end up being, for example, the first set of symbols, the zeros. So, does anybody have any ideas of what I should select for W? So anybody have any ideas? Because remember, I have to select W so it's indeed in this language, but I want to have it so that it's long enough. Does anybody have any ideas? So remember, so I'm going to have more zeros than ones in this string. That's what it has to be in this language. So I'll give you a suggestion. 0 to the P plus 1, 1 to the P. So you'd agree with me that this is in that language, right? Because I is indeed bigger than J. That means this is my I, that's J. So then since the length of W is at least P, W can be divided so that the W is equal to X, Y, Z, where the length of XY is at most P, and Y is, of course, not equal to the empty string. So what I'm going to do is I'm going to, just to make this a little easier for myself, I'm going to let the length of Y equal some value. I'll call it, let's call it L. I'm going to call it L. So what I'm going to do is I need to appropriately select the K value. Now, you got to be careful with this one because notice that I has to be bigger than J. And if I pump up, as in like I add more Y's, I might actually build a string that's indeed in the language. So I already see that. So you have to be very careful about this one. So does anybody have any suggestions of what way I should go? Should I pump up or down? So I want to push it out of bounds. That's basically what I want to do. So I violate the I is greater than j up there. So what I'm going to do is I'm going to consider the string x, y to the 0, z, which by the pumping lemma is in L less. That I know. So the real question is what I could do with this fact. So what I'm going to do is I'm just going to write out what that means. Then, well, if I have no y part, then it's just xz, right? Then xz is going to be equal to 0 to the p plus 1, right? Because remember, it's p plus 1. But remember, the y part happens in this first part. In fact, technically, I could have written over here. In fact, I would recommend doing it, is that you'd observe that, notice that y consists entirely of zeros. That's one thing I didn't write here. I'd recommend doing that if you wanted to do this a little bit more carefully than I did. But you'll notice that I've formulated here in exact terms. So then xz is 0 to the p plus 1. And then I subtract off L, because remember, I'm taking off the y part. The length of y is indeed this L. And then I have 1 to the p, right? And since the length of y is greater or equal to 1, then I look at the exponent here. I want to know if that's bigger than p or not. Then p plus 1 minus L is, now notice, because remember, p plus 1 minus this L, that's the length of the string, but we know y is in fact not empty. That means there's at least one symbol. This implies that this is at most p. So xz does not have more zeros than ones. More zeros than ones. So xz is not in the language L less, which is a contradiction. Which of course means that LS is not regular. So are there any questions about this proof? Any questions at all? Are we all good? Give me a thumbs up if we're all good. So notice that in this example, I couldn't just pick any old k value in the pumping lemma. I had to be a little bit more careful about it this time, because I needed to make it so I get a value so that the number of zeros and ones is in the appropriate amounts. So for example, in my earlier examples, I had many values I could have selected. Here, notice there's only really one I could have selected, right? I needed to just not include y at all, meaning I pumped down. So are we okay with this example? I and j, this one right here? To the left, this one? Yeah, this is a 1. That's a such that. So this is just such that. No worries. No, thank you for asking me about this. I appreciate it. Yeah, no, so that just means such that. So if you find yourself, if you don't really like the bar, you can always put a colon there. Some people like using that for that too. But yeah, no. But yeah, just be careful. That's all I'm saying about this pumping lemma example. Is just be very careful, because you want to select the string so that you get the contradiction, but you have to make sure you pick one that is in fact not going to end up in that language. So notice if I pick say for example x, y to y2, like I put 2 here in the exponent, that means I repeat y twice. Notice that I'll create more zeros than ones, meaning that it's actually going to sit in this language. So we need to pump it out of bounds. That's basically the idea, is that to do that, I have to remove y. I don't want to add more y's. But yeah, no, so this is the last example I have for the pumping lemma. Just I want to make sure I give you some tips, and for dramatic purposes, I wrote actually a list for myself, and it'll be in your notes after. So here's some tips, and let me just read this carefully because I have to do it for dramatic purposes. So it says, you cannot use the pumping lemma on a finite regular language. These are regular, right? We established that at one point, so you can't use the pumping lemma on finite regular languages. You cannot use the pumping lemma to show a language is regular. Remember, the pumping lemma is in fact a property all regular languages have. And make sure when you always select W, you want to make sure its length is at least the pumping length, P. Remember, you need to have that, otherwise you can't invoke, under an assumption that it's regular, the pumping lemma. It has to be long enough. And lastly, this is probably the most important one, and I've said this one a couple of times, is you cannot choose the decomposition of x, y, and z. The only thing you know is that the length of xy is at most p, and that y is not empty. So you must show that each decomposition leads to a contradiction. A good selection of W can often avoid multiple cases, but just be aware of this fact. So notice that the way I select W is so that I try to usually keep it all in one symbol. If you have a problem with this, then you're going to have to break it into multiple cases and then take each one individually. And then you show contradictions for each one. But yeah, so that's all I have to really say about this topic. So now we're going to transition over to talking about a different set of languages. So we're going to talk about, so up to this point we've talked about regular languages, and now I've shown you that there exist languages that are not regular. So now we're going to be moving on to another set of languages called the context-free languages. So it's like we're kind of flipping the page to a new chapter, both figuratively and literally. We're going to start talking about context-free languages. So just to make sure we are all kind of on the same page where we currently are, I'm going to draw this fun picture for you. So up to this point, we've talked about the regular languages. The regular languages. So these are all the languages in here in this box. It's quite powerful. Have all the languages in this one box. The next set of languages I'm going to talk about are context-free languages. The next thing we're going to talk about is in this dashed circle. These are going to be the context-free languages. So every language we're going to talk about is in fact going to, so all the regular languages are all going to be special kinds of these. That's going to be kind of the big thing you need to point. You're going to hopefully see this in due time. So you might ask, Dan, why do we study context-free languages? It's because there's a way we could describe them. So let me just write this. So I'm going to say these languages have a recursive way of expressing them. Called context-free grammars. Called context-free grammars. Now, I want to mention, because I always have to kind of motivate why you might be interested in these things. Because it's easy enough to just say, hey, Dan, this is enough of a motivation, and that the fact that this is beyond the regular languages. Well, I want to just kind of make sure there's some concrete meaning for this as well. So these grammars, and I must stress that we're talking more about something that's tied to the semantics of, say, programming languages. So we're moving up to something that's a little bit more expressive than what we currently have. So these grammars often are closely related to the specification, development of compilers. In particular, I'm talking about parsers. And if you're wondering what I mean by a parser, it looks at the structure of the program. So the parser looks at the structure of the program. So when I give you a program, one thing that makes things like these parsers very powerful is it gives me some way, say if I have a bunch of different ways of prescribing things in my programming language, such as the semantics of the language, these parsers allow me to kind of take everything and kind of throw them together so I have a better idea of what the structure looks like. So we're going to talk about things such as parse trees, and hopefully next class I'll show you an example of how you could kind of take a sentence or a sequence of expressions and simplify it down to its kind of bare components. So I'll show you one simple example of that next time. But I just want you to just be aware of this fact, is that these context-free grammars often are very closely related to the theory of compilers, in particular these things called parsers. So when it comes to this stuff, I have to be very careful because it gets very technical. So I'm not going to go much deeper than this. But I'll give you an example of what I mean by this. So you might ask, Dan, what does this recursive way of expressing it mean? Now, one thing that we encountered when we dealt with the pumping lemma, which we used against the regular languages that we presumed were regular, is that I was able to kind of effectively substitute in a value that causes it not to be able to be pumped, right? Well, the context-free languages allow me to substitute in any way I feel like, as opposed to this way that I kind of broke down in with the regular languages. So we're going to see that this recursive structure, this way I could describe things in this manner, is going to be a very core part of how I talk about these so-called context-free grammars. So this is going to be much closer to the following some sort of rules, and these get recursively applied. So before I get to the definition of a context-free grammar, I thought I would kind of give you bits and pieces that kind of put everything together. Depending on how far we get, we may actually get to the definition of a context-free grammar. And I assure you it's not actually that complicated. It's just, I like to give you some setup to motivate what exactly it means. Because it's very easy to just be like, hey, look, here's the definition, just there you go. I want to kind of motivate it for you. So grammars, I want to be clear just more broadly what a grammar is. So grammars consist of a collection of substitution rules. Substitution rules called productions. That's the first thing you need to know about grammar. So these productions have some parts to them. So the first thing is that there's going to be a variable. So each production has a symbol called a variable. Sometimes these are called non-terminals. So if you ever hear me say the word non-terminal, I mean variable. So these are going to play the role of representing a language within the expressiveness of the context-free grammars. So these are often going to be written with capital letters when I use them. And in the context of a production, it is often called the head. Called the head of the production. So there's going to be three parts to the production. The first part is I give you some variable. It's going to be usually a capital letter. And I'm going to call that the head. We're going to often sometimes have it where we have multiple production rules with the same variable. And we'd often will try to lump them together, as you're going to see a little later, as sort of a convention. So next you have an arrow. So this is the next part, is an arrow. This is often called the production symbol, if you want to get a little bit technical about this. The production symbol. And then the third part is the body. So the body. So the body of the production rule is just simply a string. A string of 0 or more variables and other symbols called terminals. So they're called terminals. So there's going to be a bunch of these other symbols. Now, you might ask, Dan, what are these going to be about? So you remember, like in our DFAs, our regular expressions and whatnot, we always had this input alphabet, right? We had some sort of alphabet that we worked over. That's what these terminals are going to be. They're going to be symbols that belong to some set. This is going to be about the equivalent, if you think about it, as your input symbols or your alphabet that you work over. So just think of the input alphabet when you see terminals. So then there's going to be a special, so one of the variables will be designated the start symbol or variable. So it's start symbol or variable. And this is often written as the top rule in the context-free grammar. So I'll be listing these rules from top to bottom. If it's never stated explicitly, just assume the one at the very top is, in fact, the start symbol or variable. The start variable or start variable. Yeah. The start symbol or variable. I'm getting a little excited here. I'm looking forward to showing you this example. So these are just kind of what you need to keep in mind. These three parts to each production rule, and then there's going to be one where we're going to effectively start. So let me do the example here, and then we're going to see all these pieces, how they play. So here's an example. Consider context-free grammar. Context-free grammar G1. So I'm going to call it G1. And this is how I'm going to define this context-free grammar. So I give you a set of production rules. And here we go. So I'm going to start off with giving you a variable. I'm going to call it capital P. Then the arrow is going to be indicating the production symbol. And then I'm going to give you the body of my production rule. So remember, this is going to be a string of 0 or more variables or other symbols. Call these terminals. So the body of this one is going to be 1A0. 1A0. So that's the first rule I have. The second rule is that the body of the second rule, it's also going to be variable P. It's going to go to this other one called Q. Q is another variable. And Q, its body is going to be the symbol 2. So I have three production rules here. So if I want to talk about what the variables are, so the variables are P and Q. So that's the first thing you should know, is that P and Q are the variables here. The terminals the terminals are 1, 0, and 2. If you're a little bit of a neat freak, kind of like me sometimes, you'd probably be compelled to write 0, 1, 2. And don't worry, it's okay. And of course, can somebody tell me what do you think the start symbol or start variable is? Can somebody tell me based on what I drew here and what I just said before? P. Yeah, it's P. Very good. And of course, P is the start symbol or start variable. I'll just say start symbol right now. Okay, so this is just an example of a context-free grammar. Now, I want to tell you how you use the context-free grammar. Now, this is where things get a little bit fun and why I really like context-free grammars. Just as actually a fun aside, when I was an undergrad, I got really obsessed by these context-free grammars. And I originally was using it to try to design an algorithm for generating combinatorial objects. It was actually one of my first papers. And I was doing this for my undergraduate thesis at the time. And I was trying to derive a way to generate them by trying to exhaustively use these context-free grammars. And it ended up, the algorithm was much simpler than what I was doing with these context-free grammars, but generally it was a nice flexible way for me to think about what I was doing. In that case, it was a very recursive object I was trying to describe. So I want you just to be aware of the fact that when we're going to talk about this, it's going to look very recursive. That's hence why I've been saying this over and over again. So you're going to see that the way I'm going to talk about this is going to be a little bit more careful. It's not going to be where I'm just going to be simply saying, hey, look, guys, I just apply the substitution. It's not just going to be that. It's going to be that, like, I'm going to build strings like top, bottom. But I just felt like telling that story. It's just that context-free grammars are very expressive. That's why a lot of people like using them for programming languages, because you can describe the semantics or structure of a program using them. Just as a fun aside, if you're familiar with the XML format, a lot of the earlier work with XML was built on context-free grammars. So if you're just kind of curious, like, oh, what kind of killer apps does this thing have? Like, you ever wonder what, if you're familiar with XML, you might recognize it as some sort of like tree-like structure. It relates to this. So I'm not going to go too much detail about that because there's some technical aspects of it, but I just feel like I wanted to motivate this. So if you've heard of XML or have seen or used it before, you may be familiar with this tree-like structure. That same thing's going to happen here. So I'm going to describe to you how you kind of work with this grammar. So the grammar describes a language by generating each string as follows. So I'm going to give you a series of steps, and this is how we're going to generate a string. So notice that the language I'm using here is that I'm going to have a bunch of rules, and the production rules are used for me to generate a string. And all possible strings that I could generate forms the language. So here's kind of the rules for this. So you begin with the start symbol. So begin with the start symbol. So you write this down. So for start, you write this down. So you write this down. That says down. Now what I'm going to do is I'm going to find a variable that matches the one that I currently have, and I'm going to write down the body of its production rule. So I'm going to replace that variable with the body of that production. So find a variable that is written in the body of its production rule. Replace the variable. So you just find some variable in there, and you're going to replace the variable that you've identified with the body of the production for that rule. Like I said, it's going to be very recursive. So now I'm just going to, step 3 is very simple. I'm just going to repeatedly apply step 2 as long as there are variables. As long as there are variables. So for anybody that has a little bit more of a background with theory of computation, you may have heard of things called string rewriting systems. This grammar is an example of such a thing. So here's the idea. I start off with the start symbol, so I just imagine that is just there. It's just there. So for example, let me say I start off with P. Say for example, here's the start symbol of my example. And now there's 3 rules I could apply. There's 3 rules. But there's really only 2 that I could use for this symbol, right? For P. So one example is that if you look at the top, there's 2 production rules for P. There's one that leads me to Q, and then I substitute that with 2. Or I could substitute in the following. So I'm going to look at, find the variable here. And this is right now what I have. I'm going to replace this variable with the body of a production rule for that. Actually, for that rule, I think it's for that symbol. Symbol or variable. Sorry about that. It's for the variable or symbol, right? You identify a variable, then you replace it. So what I could do, and I'm going to use this double arrow to suggest that I'm going to apply a production rule. So I'm saying that I'm deriving from that symbol a new body, and it's going to apply one of the rules. So here's an example of one. So remember, this is the first rule of my context-free grammar, 1P0. That was the first one. I replaced P with that. And now what I could do is I could replace P with another first production rule, or I can use the second one. Here, what I could do is I can replace P with Q. So I have 1Q0. And there's only one production rule for Q. It leads me to 2. So I look at that and I see, okay, well, I replaced the Q with a 0. This is one example of a string that gets generated by the context-free grammar I have over there. But let me show you how wild this can get. So I could start off with P. Then I apply the first rule. Then I apply the first rule again, but remember, P's right here. I'm going to replace that with the body of the production rule. So I replace P with, I could do the following. 1P0, 0. So am I losing anybody right now? So I've replaced P with the first production rule again. And now I'm going to do it again. So I get 1, 1, 1, P, 0, 0, 0. And of course, I could switch the P to a Q if I like. So 1, 1, 1, Q, 0, 0, 0. And lastly, I end up with, when I apply the rule for Q, I get 1, 1, 1, 2, 0, 0, 0. Let me get out of the way. So do you see how I can keep repeatedly applying the rules over and over again? So when I have a production rule, all I do is identify the variable and I could substitute that in with the body of its rule. So just as another example, just to make clear, So I can go from P, instead of going from the first one in the first row, I can go right for Q if I felt like it, because it also is because P is the start symbol, right? I can go right to Q, so I can turn that P right into a Q and get a 2. So all possible ways I could substitute using those rules so that all of them end up being terminal symbols, all possible ways I can generate them, that's going to end up being what the language is going to look like. I'm going to formalize this a little bit more probably next class. But we have any questions about this? So this arrow just simply means I'm applying a production rule from here to there. Are we all okay with this? Give me a thumbs up. I just want to make sure we're all good. Okay. So now I'm going to move over here. Okay, excellent. I see some thumbs up. Okay, good. So I want to show you that there's another way you can look at this, but I'm just going to I want to formalize what I just described over there. So let me do that first, and then I'm going to show you actually a very nice way you can think about. So I'm going to keep this example here for now. I just want to define one thing for you, and then we're going to see a way we can actually visually look at what's happening. This should connect to something I briefly mentioned about XML. So, just to be formal here, rewrite. So we write U derives V. U derives V. That's an R right there. Derives V. Denoted U with the right arrow with a star above it. V. If either U is equal to V, or there is a sequence, U1, U2, U3, all the way up to UK for some k greater or equal to 0, where you do exactly what I did over there on the right board. So I just start off with U, then I do the derivation, then I go to U1, then I go to U2, then I go to U3, and so on until I reach UK, which then derives to V. So this star is a nice simple way for me to contract all of these derivations. So when I draw that arrow, that means derives or derivation. But when I use a star above it, it's basically me saying I can go from this string to that string through these derivations. So, excellent, we have just enough time for me to do this. Okay, there's a nice simple way of actually me representing how we do the derivations graphically. So for those that are more visual with things, this is going to be kind of handy. So a graphical way to represent a derivation is using a parse tree. You can tell I was getting excited about this all day, using a parse tree. So there is a formal way for me to describe the parse tree to you, but I'm just going to explain it verbally. I have a more careful explanation in the notes, but I want to do an example just to illustrate this. So you recall I gave an example over there where I had, I believe it's 1, 1, 1, 2, 0, 0, 0, where I applied the P rule at least a few times, right? So another way I can look at this is I imagine I start off with the start symbol, and then I apply the derivation rule for P, which is going to get me a 1 and a 0 on the end. But remember, the middle symbol was a P, right? So each one of my internal nodes of this tree are going to represent variables or terminals. Those are basically the only two options. So I start off with a start symbol, I apply rules. So I'm going to be describing the rules using this parse tree. So if you're having a hard time following me, just take a look at the notes after class for the more careful explanation of how this works. Don't worry, we'll see more of these. So if this first time it doesn't click, we'll see another one. So I apply the P rule, I end up with 1P0. That's exactly what I had before, right? Now, if I apply the same rule again, you'd agree with me that it should be another 1P0. But remember, it's within the context of when I applied the original first rule again, that one over there. So that one was 1P0, but I've substituted the P now for 1P0. Well, I could do this again if I want. 1P0, right? And I can replace P with Q. And then Q gets replaced with 2. Now, the one thing I really want you to notice is that the leaves of this tree, which are the 1, 1, 1, 2, 1, 2, sorry, 1, 1, 1, 2, 0, 0, 0. These are the leaves of this tree. Notice that if I concatenate the leaves of my tree, I end up getting the string. Is that kind of cool? So notice that I'm describing this process of providing the production rules as links in a tree. So notice that this is just a symbol. I've drawn it this way to make it a little easier to see. It doesn't have to look like this. But notice I can keep repeatedly applying the rules. And I know when I'm done, when I have all the leaves being terminals, and I haven't talked yet about them, but epsilon, because there can be epsilons as well. But anyways, are there any questions about this? So the whole idea is I'm just applying this rule a few times, and then I apply this one, and then I apply that one. But yeah, so this is a nice graphical way you can actually visualize the process of me doing these derivations. So this tree has nice properties. I must note that you don't necessarily have to start at the root of the tree being the start symbol, which is what I did here. You can start really anywhere. So that's just something I need to make a remark about. But other than that, when we come back next time, we'll talk more about context-free grammar. I'll give you one more convention, and then we'll actually get the definition for context-free grammar. Okay, everybody? So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later. And I apologize again for the fun technical issues.